Hi, everybody. Welcome to the APES virtual classroom. I'm glad that you could join me again. I'm Ms. Fassler, and I teach APES in Marshfield, Wisconsin. Let's start with the homework that you did last night. You looked at a question that was a really great combination of some energy and sustainable design ideas. The students at Fremont High School want to plan a new green building. And so the first prompt that I asked you to look at was to identify one way the school's heating system is likely to add to the school's carbon footprint. You were told in the article that the school used fossil fuels, and so there were really only two ways that it could contribute to the carbon footprint. Remember that we always have to burn or combust that fossil fuel, and it could either release carbon dioxide or incomplete combustion of that fuel could release carbon monoxide. Only two possible responses. Next, describe one realistic way to reduce the contribution of the heating system to the school's carbon footprint. And the key thing I want to point out on the rubric here is that you couldn't just say, oh, one thing that the school could do would be to use solar energy, because it didn't necessarily state that they quit using their fossil fuel. So it would have to be switch to a more renewable form of energy, decrease the temperature of the thermostat. You could have gone for purchasing carbon offset points or offset credits. And then there was a whole range of different things you could have mentioned having to do with the efficiency, passive solar, or the green roof or double pane windows, south-facing windows. When you are looking at your notes and starting to make your lists and organize your notes, keep in mind that you don't need to have every example that's listed on a rubric. You want to pick ideas that kind of make sense and resonate with you and that are going to get you targeted right to a good solution. Next was to identify two environmental benefits of a living green roof. We talked about a few of these, and there's a few on here we didn't specifically mention, but you may have used. We talked about the fact that it provides insulation and could reduce heating or cooling costs. It's an area that I could produce locally grown food. We talked about it filtering stormwater runoff or reducing the amount of runoff. Then you'll see a few other examples as well. You can always, and I suggest that you go through some of these lists in a little bit more detail when we're done, and you can process things a little bit. And again, pick out examples that are really meaningful to you. Describe two practices the cafeteria's food service could use to decrease the environmental impact at Fremont High. And notice that that term describe, I have to make sure that I'm describing. I can't just identify the practice. I can't just say offer more vegetarian options. I have to make sure I describe how that's going to decrease my environmental impact. For example, I could use locally sourced foods, which would decrease the amount of gas that I had to burn in transporting that food great distances. I could compost my food waste, which would decrease the amount of waste going to a landfill. And again, lots of options here. Pick out a couple that kind of make sense to you, maybe things that you're already practicing or that your school's doing. I like the idea of the refillable water bottle stations. Next, discuss two benefits of using native plants for landscaping at Fremont High School. We mentioned a few of these yesterday. Remember, most of them kind of focus around the fact that those native plants are better adapted to their environment. Therefore, they need less pesticides, less water, less fertilizer. And again, because I'm discussing that benefit, I'm stating something and then discussing why that is a benefit. That because is a real nice transition term there. You can see a few other examples that they gave as well. And finally, in letter E, during the renovation, the carpeting is going to be replaced. Discuss one environmental benefit of using flooring made from plant materials such as cork or bamboo instead of carpet made from synthetic fiber. And again, half of the battle, guys, is making sure you read that question really carefully, because if I didn't read and take the time to process what the question was really asking me, I really decrease the likelihood that I'm going to answer it in an adequate way to earn a point. So I had to make sure that I was doing a comparison. In other words, plant material like bamboo is more compostable or biodegradable than the synthetic fibers of the carpeting. The plant-based materials require less fossil fuel or toxic chemicals in production than the synthetic fibers of the carpet. So lots of different options you could go with there. Our discussion today on air pollution is really going to focus on this point that you may be still a little bit iffy on. So where are we going today? Well, first of all, remember your 2 questions on your exam on Monday, May 18th. And Dr. Sowell and I have been kind of starting to prompt you about what that day is going to look like. You've been getting emails from the College Board about helping you start to prepare for that. And we're going to have more tools and tricks and tips for you as we proceed through the next few days. So today we are starting in on Unit 7 on atmospheric pollution. Air is a natural resource that covers the earth and crosses many system boundaries. That could even be geopolitical boundaries. And it's what makes air pollution really different than other kinds of pollution. The air is a commons. So if, for example, I'm exposed to a toxin in my drinking water, I might, well, that's a bad situation. And while I'm working on remedying that situation, I have an alternative. I could maybe go buy bottled water, or maybe my community is trucking water in that I can go to a station and fill big jugs. But if there's a toxin in the air that I'm breathing every minute of every day of every year of my life. And there's not really anything I don't have a lot of control over some of the pollutants in air, and not oftentimes a good strategy to avoid that. We'll take a look at the difference between indoor and outdoor air pollution. And today, as we go through these first 4 topics, we're really going to focus on that outdoor air pollution. And then tomorrow with Dr. Sowell, you'll wrap up all of the review by looking at indoor air pollution. Let's begin with sort of a general overview to remind you of some of these different pollutants and where they come from. Remember that a primary pollutant is something emitted directly from its source, and usually that's combustion of some type. It could be these things like carbon, sulfur, or nitrogen oxides. It could be a hydrocarbon. That's what we're talking about when we use that acronym VOCs, volatile organic compounds or chemicals. We're going to look at them in a little bit. A primary pollutant could be a suspended particle. We're going to refer to that as particulate matter. Sometimes the source of those primary pollutants is a natural source. We did a quick review when we were looking at new carbon yesterday, and said volcanoes have this tiny little trickle of natural carbon dioxide. It could be from combusting gasoline in my vehicle, a fossil fuel. So certainly I get carbon dioxide. The main other oxide gas from gasoline is NOx. Here's a coal burning plant that releases carbon dioxide. We tend to label coal as releasing mostly the SOx compounds, gasoline mostly NOx. There's also that particulate matter and some heavy metals present in coal as well. Not that those compounds can't be present in all fossil fuels, but our APES curriculum tends to kind of classify NOx mostly from gasoline, SOx mostly from coal. And then we have these secondary pollutants that form as a result of other gases in the atmosphere reacting. We're going to focus today on only one secondary pollutant, ozone, and then you'll look at some of those acids tomorrow. Let's just do a quick checkup of those oxide gases. All of these are those primary pollutants, and make sure that you're clear on a source and a human impact. And again, kind of modeling for you how you want to organize notes for this unit on air pollution. What's the pollutant? What's the source of it? Where does it come from? Can I describe the process by which that gas gets into the atmosphere, and then some of the impacts of it? We talked about carbon monoxide in the footprint of Fremont High. Remember, that's when my furnace or my gas isn't being burned at quite high enough temperature, or something's not working right, and instead of carbon dioxide, I get carbon monoxide. The thing about carbon monoxide, you're going to see a lot of common human health impacts for all of these pollutants, a little bit generic, some of them more specific. But the thing about carbon monoxide is it interferes with the ability of hemoglobin to transport oxygen. So my brain gets deprived of oxygen, and it could lead to unconsciousness and even death. Carbon dioxide, we had the natural source from volcanoes. We certainly get it when we have decomposition of organic matter or cellular respiration. But remember from our carbon cycle diagram that the combustion of hydrocarbons, of fossil fuels, is a disruption to the carbon cycle and is adding carbon dioxide that has no process that complementary removes it. Sure, photosynthesis removes CO2, but there's not enough plants to keep removing all the additional CO2 that we're adding. There's no direct human health impact of me breathing carbon dioxide, but certainly many increased death rates linked to global warming and climate change as a result of adding more carbon dioxide. These SOx molecules, we want to avoid committing to a subscript here. There's a lot of pretty complex chemical reactions going on here. And as an introductory college level environmental science course, our goal is to give kind of a broad overview of these processes. And in a more advanced chemistry class, you'll dig into the detail of those reactions. So these sulfur oxide compounds come from combustion of fossil fuels, mostly coal. And again, you can see the list of potential human health impacts. And the nitrogen oxide compounds, mostly gasoline, and similar human health impacts. We're going to talk about all these more as we move through the lesson. Let's look at one quick question that's two simple parts of a prompt from last year's free response test. The visibility in national parks can be affected by many different air pollutants. And my graph here, there's some calculations they did on the graph last year, but it's showing me 4 big national parks and the visibility in miles. And the historic visibility, how far when I'm standing on the top of the ridge, how many miles can I see? And I can see that based on an average throughout from historical data, that visibility has greatly decreased. The National Park System recognizes this as a pretty big problem and is looking at some ways to mitigate it. But because visitation is up and we all like to drive our cars through the park, there's a big decrease in visibility. One primary pollutant, that should be pretty easy. You could have listed any of the carbon, nitrogen, or sulfur oxide compounds. There's a few others there. Like I said, we'll look at VOCs and particulate matter in more detail. And then describe how that primary pollutant becomes part of the atmosphere. Got to have a verb there. And if it's something to do with fossil fuels, I have to burn or combust them. So you can see that that's mostly, I'm guessing where most of you went was something about burning fossil fuels, releasing those. The next topic that we're going to look at is photochemical smog. And you probably remember this is one of the more challenging topics. This is a perfect example of where hopefully in your college level chemistry class, you get an opportunity to dig into the process in a little more detail. So the term photochemical smog, that's kind of like a soup, a mixture of really harmful pollutants. The major component of that is ozone. And we can use those terms synonymously. If I'm writing about this on an FRQ, I can say ozone or O3. I can say ground level ozone. We refer to that as tropospheric ozone to distinguish it from the good stratospheric ozone that blocks incoming UV radiation. And I can just call it smog or photochemical smog. So the first thing we want to do is identify the reactants. What are the ingredients that are necessary to form this ozone? Well, the first thing I need is that NOx that's emitted from the gasoline. I need volatile organic chemicals, VOCs. And if you see the acronym VOC on the exam, of course, they're going to tell you what that means. If you just want to write about VOCs, you can use that acronym. And we're going to dig into that in just a minute. And finally, I need sunlight. The photo part of the term photochemical smog is the fact that sunlight is involved. So that's pretty straightforward. 3 different things: NOx, VOCs, and sunlight form ozone, O3. Now what we want to do is focus on describing the process, just like we identified a primary pollutant and then described the process by which it got into the atmosphere. Now that I know what those ingredients or reactants are, I have to describe how that gets turned into ozone. So the first thing is the sunlight. This UV light strikes a molecule of NOx and it kicks off an individual atom of oxygen. That individual atom of oxygen combines with a molecule of oxygen gas. 21% of our atmosphere is oxygen, so there's plenty of that going around. And all together then, oxygen, O, plus O2 yields O3. So if I'm going to describe the process, oh, wait a minute. You're probably going, hey, Fassler, what's the deal here? You keep talking about those VOCs, but you never described how those enter into the reaction that makes ozone. So this is where we need to make a clear distinction between simply identifying that VOCs are important in creating photochemical smog, that's that soup of chemicals, and being able to describe this 2-step process by which ozone forms. Let's repeat that to make sure you have it down and you can get that in your notes. Sunlight, light, UV energy strikes a molecule of that NOx gas emitted from gasoline. That knocks off an individual atom of oxygen that combines with O2 to form O3. So you could probably have that equation in your notes as well. What happens then is this is a secondary pollutant because it formed between these reactions in the atmosphere, and it's a pretty nasty pollutant. I have some of these very similar human health effects that I talked about from exposure to carbon monoxide or NOx or SOx, but I'm adding a couple other things here. I'm starting to look at increased chest pain and pulmonary inflammation, increased risk of heart attacks. So now I'm going from kind of respiratory things to cardiovascular. Hold on to that thought because we're going to dig into that in a little bit more detail when we look at particulate matter. So even though I don't need to know the complex series of reactions that are going on with those volatile organic compounds in photochemical smog, I just need to identify they're an ingredient. They're still a primary pollutant and pose problems in and of themselves. So let's break apart what this word, this acronym volatile organic means. Volatile means, a lot of kids think that means like it's flammable, but oftentimes volatile liquids are flammable, but volatile means it'll easily evaporate. It will really easily go from a liquid to a gas. Like water evaporates, a puddle evaporates, and it's water vapor. An organic compound, a hydrocarbon, like here's a benzene ring, they have pretty low intermolecular forces of attraction holding them together. There may be low molecular weight, and they will really readily go from liquid to gaseous phase. Remember, anytime that substance gets into the air that I'm breathing, I'm getting constant exposure to it. And that's why VOCs, while an issue in outdoor air pollution, are really a big issue with indoor air pollution. We've already talked about these kind of indirectly when we talked about green building, sustainable building, and that was that point on the rubric about replacing the carpeting in Fremont High School, and the fact that a natural material versus a synthetic material that has these organic solvents in it or organic fibers in my carpeting is going to be a lot more sustainable, a lot healthier for me. So it could come from everything from my building material, the varnish in the wood of flooring or the glues that are used or the paints. It could be cleaning products that I use. If I spray something and like, ooh, that kind of has a nasty smell to it, ooh, I can feel that. That means that it's a volatile organic solvent in that cleaning product. And when you spray that, you inhale it. Some of the health effects associated with VOCs, again, you should have in your notes a statement that makes sense to you about increases respiratory problems. It doesn't necessarily, some of these pollutants don't necessarily cause asthma, but they can bring on an asthma attack, or they can exacerbate or make worse the symptoms of my asthma. One of the things about VOCs is because these are organic compounds, some of them, like benzene, is a known carcinogen. It's a cancer-causing agent. But I want to be a little careful because very few, like NOx and SOx, they don't cause cancer. So if I'm organizing this information in a chart, sometimes students kind of like to stick to a rather safe, broad description of a human health effect, unless you want to break down individual gases or pollutants that have different kinds of impacts and what they are. The solutions seem pretty straightforward. Well, I just don't use certain cleaning products, or I don't live in a house that's been made with those things. But unfortunately, if I'm renting an apartment or living in a dorm room, I don't always have much of a say in the type of building materials that I use. So that's often a little difficult. In terms of mitigating, if it is a problem, I could make sure that I'm venting my home a lot, or purchase an air purifying system. I'm pretty sure Dr. Sewell will go into some detail on that tomorrow. I just wanted to share with you, we're going to talk about the Clean Air Act in just a second, but I wanted to give you a little historical perspective because we're living in a climate right now where there seems to be a real push towards deregulation, and this idea that environmental regulation and economic growth can't be synonymous and live hand in hand. And we know that's not true. We know that as the Clean Air Act and all of our other major legislation was passed, GDP just kept going up and up and up. So these are images from the city of Los Angeles. The Los Angeles Public Library has a great archive of some photojournalists documenting what the air quality was like. And it's important for your generation to realize how bad things were before we passed the Clean Air Act and the Clean Water Act. I'm old enough as a child to remember a time before the Clean Air Act and the Clean Water Act. And I can remember coming out in the morning and being able to literally brush particulate matter off a vehicle that sat outside overnight because there wasn't any legislation on that. And here are people wearing retro throwback gas masks, and young people actually petitioning at a city council meeting to improve air quality. This is an image from the Empire State Building in New York City, and it gives you that idea of visibility. When we talked about how visibility in the national parks has decreased, this is what we mean. There's so much pollution in the atmosphere that it limits my ability to see through that cloud of smog. So the Clean Air Act, as you probably remember, is one of our major US cornerstone pieces of legislation. It was passed in 1970 and overwhelmingly supported by the public, by politicians. Everybody agreed that the scenario that we witnessed in those previous pictures was unacceptable, and we needed to do something about it. And it identified these 6, what we often refer to as common pollutants or criterion pollutants. I told my students, and maybe your teacher did, if you remember the acronym NOS CLAMP, it's the 6 pollutants: NOx, ozone, SOx, carbon monoxide, not carbon dioxide, lead, and particulates. And look at the amazing results. There's nobody that could argue that the Clean Air Act was hugely successful. The amendments and the 1990 Clean Air Act amendments went even further in starting to address things like acid rain and protecting the beneficial stratospheric ozone. Unfortunately, since 2016, we started to see an increase. We're going to look at particulate matter in a second. We started to see some of the levels of these criterion pollutants start increasing. And one of them that we're really concerned about is particulate matter. So as we start to deregulate and kind of roll back some of these precautions that are put into place to protect us, we will start seeing a lowering of life expectancy. The Centers for Disease Control can quantify the loss of life expectancy because of respiratory and cardiovascular disease associated with breathing polluted air. Let's do a quick question or two that looks at the topics that we just addressed. One that deals with this kind of complex issue of ozone formation. Nitrogen oxide is produced early in the day. Ozone concentrations peak in the afternoon and are higher in the summer because ozone is produced by chemical reactions between oxygen and sunlight. And I wanted to point out, if we looked back at that first slide with the all the cloud of primary pollutants, we would see both NO and NO2. And technically that NO gets converted like as the morning goes on. So I've got like, oh, people leaving and driving to work and the office and school, and they're emitting a lot of that NOx. One of the reasons us APES teachers tell you just to use NOx is we don't want you to commit to a subscript there. They're not gonna, again, these chemical reactions can get pretty complex, and we're not gonna necessarily have to tease out that first it's NO and then that gets converted to NO2. So let's, oh, what are those other things on there? Aldehydes, hydrocarbons, those are the VOCs. So we have NOx, we have some sunlight, and we have VOCs. So notice that a short time after those cars all started driving during that morning rush hour, and pretty soon the hydrocarbons peak, and shortly after I get a peak in VOCs and NOx, the level of ozone starts going up. I use the VOCs and the NOx to create the ozone, and those concentrations go down while the concentration of ozone goes up. So I've kind of given it away, but there was a lot to break down in that diagram. Which of the following best explains the pattern in NO concentration? I'll see if you can take a look at that one. And you should have got that. That was produced by rush hour traffic. Again, you don't necessarily need to be able to describe in an FRQ that that original NO was oxidized into NOx. All you need to conceptualize is what we looked at earlier. NOx is emitted from burning gasoline, and it forms ozone, and that ozone is going to peak a little bit later in the day. The last primary pollutant that we'll take a look at, I think it's the last one, is particulate matter, or PM. This is solid particles of dust or ash, what we call fly, could even be liquid droplets. It comes from burning fossil fuels. It comes from burning biomass. If you've ever had a campfire and you're burning wood and a breeze comes along, you might see a lot of that ash and fly coming at you. Forest fires are a big contributor to particulate matter, and even cigarette smoke, because there's a lot of nasty stuff in there that's releasing particulate matter. Oh my gosh, look at those human health effects. That looks pretty straightforward. The thing about particulate matter is that other substances can kind of stick on to those little particles of dust or ash or fly, and then they can be carried by wind currents and deposited. That verb is deposition. They can be deposited or fall out, just like rain, right? They can be deposited a great distance from where that particulate matter was actually generated. When we look at this image, these are not the actual sizes, it's a size comparison. So you can probably picture the size of a fine piece of beach sand, And then relative to that, a human hair, a dust particle, and this is a little tiny soot particle. And on the next slide, we'll look at this in detail. The smaller the diameter, the smaller the size, that is measured in picometers, the smaller the size of the particle, the more harmful it is. And at first you might be like, well, I think if it's bigger, it's going to be more harmful. So we'll explain that idea in just a minute. We know that cuts to the Clean Air Act have added to people, that the Clean Air Act has added to people's lives. And again, because we are now increasing that particulate matter again, we hope we don't see a reverse in those great trends that we've established through the passage of the Clean Air Act to begin with. Let's take a look at what happens when I breathe in this solid particulate matter. It's a really dangerous pollutant. Even though my respiratory system has some natural defense mechanisms to block these things, think of like the hairs in your nasal passages, the smaller the particulate matter, the deeper it can work its way into my respiratory system, so that this tiny little particulate matter is actually getting into my lungs. So it's not like if I'm breathing in air where there's a lot of photochemical smog, I can feel that when I breathe it in, it hurts my lungs, but then I'm exhaling that. And it's not that like that gas can't hurt my lungs and cause some damage, but it's not becoming permanently part of my respiratory system. This particulate matter can be embedded in my lungs. And this is where we start getting into cardiovascular disease and pulmonary issues, because this is in these little alveoli of my lungs is where that gas is exchanged, carbon dioxide for oxygen, and that particulate matter can embed itself in those tiny little vessels and constrict them. It can cause inflammation, it can constrict them, and my heart has to work really hard to pump blood through that constricted blood vessel. So particulate matter is one of the most dangerous of the air pollutants, and really one that we think probably contributes to a lowering of life expectancy to the greatest degree. So once we get all of these pollutants, mostly in an urban area, but rural areas aren't excluded from that. Remember, particulate matter could be soil or dust off of an exposed crop field that I might be getting exposure of air to. I mentioned that we do frac sand mining in Wisconsin. There's a lot of concern for people that live in the area where that sand is mined, that there's a lot of particulate matter in the air, and they simply want somebody to do testing. It's really the value of long-term research, because if we don't know what normal is, we don't know when something exceeds normal. So that idea of long-term monitoring of, in this case, air quality is really important for environmental and human health. So in a temperature inversion, the first thing before we review this is a natural process. What I'm describing to you, whether it's without the inversion or with the inversion, this is a natural climatic event or process that happens in certain areas under certain conditions. The deal is when a thermal inversion naturally forms, any pollution that's in that air gets trapped at ground level. It's not dispersed. And that just means I'm getting a really high concentration of that toxin. So without a temperature inversion, the sun strikes the earth and it warms that air mass near the surface of the earth. We reviewed all this when we looked at weather. And then that warm air mass that's less dense rises. Each of these is a little particle of pollutant, and it disperses all that pollution. It's not like it poof disappears and the pollution was never there. But if I'm down at that ground level breathing that, the dose or concentration that I get is much smaller than if I'm breathing that air during a thermal inversion or a temperature inversion. So what happens here is I have a high pressure system, a normal weather event, and that high pressure pushes down. It's the pressure of all those gas molecules pushing down in the air, and it traps this layer of dense cold air at the bottom. And what happens is it prevents that air mass from rising and dispersing those pollutants. So the inversion a natural climate event, but if it happens in an urban area where there is a lot of smog, it means that people that live in that area are getting a very high dose or concentration during their normal breathing of those toxins. Let's look at the same scenario, not in a city, but in an area where there's mountains, for example. Again, I have a high pressure system, all that air mass pushing down, and I have forest fires or industry or a lot of vehicle traffic, and people that live in that area are literally choking on that smog. They're getting a high dose or concentration of it. So thermal inversions or temperature inversions are the biggest issue in large urban areas that have a lot of vehicles and that have a lot of sun, because I need sun for photochemical smog, and areas that are warm and dry. That's something you might want to write in your notes. All chemical reactions happen faster in a warm, the warmer it is, the faster that reaction happens. And if I have an area that gets a lot of precipitation, again, the pollutants don't cease to exist. They don't just disappear, but I can sort of wash the atmosphere. And so if I have a lot of those chemicals in the atmosphere, I can sort of wash them out. They may end up falling as acid rain. That's not a good thing, but I'm not breathing them in. That's why a lot of large urban areas, to mitigate some of these problems, may actually do cloud seeding and try to get it to rain to sort of cleanse the atmosphere. This would be representative of what happens in the city of Los Angeles, infamous for its photochemical smog because of a lot of vehicles. And these are the San Gabriel Mountains, so they're blocking the path of that wind. And I get this cool sea breeze coming in off the Pacific Ocean, and it creates this inversion. To invert means to flip. Normally I have warm, then cool air, and the warm air can rise. I flip those layers and have the cold layer of air on the bottom. I think I have a question or two that checks our understanding of that. So I'm going to give you a second to read this question and look at the diagram. And you should have picked that the less dense warm air creates the inversion. Since we're not doing any multiple choice questions on our exam, I'm not going to take the time to talk about multiple choice strategies. Just think of how they could ask this question of me on an exam. I could identify the pollutants that are required. I could be asked to describe the process by which a thermal inversion forms. And so in your notes, it's a couple of simple steps in order to describe that process. Oh my gosh, there's a lot going on there. We'll come back to that color highlighting in a minute. Let's just read the question and answer it to begin with. An air pollution sets up some air pollution monitoring to measure the particulate matter, PM, leaving a farmer's field after crops were harvested and the soil was bare. She set up high volume air samplers 10 meters from the edge of each square field and collected samples weekly for 2 months. When she looked at her data, she was surprised by how much the PM levels varied, both from site to site on a given day and over time at each site. Which of the following parameters would have been the best to measure to help her explain the variation in her results? And again, let's reread the variations. She was surprised how much the data varied from one site to another and from one day to another. And hopefully you selected wind direction and speed. That's going to influence how much of that particulate matter blew off and was collected by her air collection sampling device. The next thing I want to do is, the next thing I want to do is take a look at the parts of the description that I've highlighted and use this as a good opportunity to talk about experimental design. Remember, one of our learning targets early on was to describe an aspect of a research design and or method used. And when you look at that, I think a lot of students aren't really sure, what do you mean by a research method, design, or measure used? Well, the research question is kind of what she's asking there, highlighted in yellow. I could actually ask that as a hypothesis. Maybe I presented this scenario and they said, based on this, what would have been the researcher's hypothesis? And I'm really focusing in on, she wants to look at the particulate matter level after crops were harvested and the soil was bare. So my hypothesis might be that the field with no cover would have a greater amount of particulate matter than a field that had a cover crop left on it. There'd be less wind erosion and that soil blowing around. The measure that she used, she took air samples, high volumes of air samples. The research method that she used, she collected samples weekly for 2 months. So she had some specific parameters. And those are the kind of things you might be asked to give in an FRQ. It might say, describe your research method. And you want to make sure that you're collecting enough samples over a long enough period of time. They might ask me what the independent variable is. We've seen that a lot. That would be the measure of the amount of particulate matter and what her control would have been. Oh, that would have been the field that still had the crop on it, because I want to measure, maybe my question is, what's the value of maintaining a cover crop? And one aspect of that value might be reducing particulate matter and the human health effects associated with that. I put this question in, I think we've sort of addressed it before. Dr. Sowell may address this tomorrow as well, but we've talked about burning wood or burning biomass and relate that to particulate matter. And the question here is, one negative impact of the practice is that impact on human health. Which of the following describes a strategy for mitigating that problem? And that would be installing an effective ventilation system. I think I mentioned when we looked at burning wood or biomass that might be even installing a chimney in many developing parts of the world where they use wood or biomass. So we have covered all of the first part of air pollution today. Just a quick review. We looked at coal combustion and the specific pollutants that are released from that. Fossil fuel combustion in general. You're going to go, I didn't even talk about acid rain because I know Dr. Sowell is covering that tomorrow, but we spend a lot of time talking about the process that creates photochemical smog and identifying the ingredients necessary for that. We talked about the human health impacts of it. We looked at the Clean Air Act, and then we looked at carbon dioxide, particulate matter, and what happens during thermal inversions. These were the skills that we really focused on. We looked at the relationship among variables in the data. When we looked at that NO to NO2 to ozone graph, how those concentrations change throughout the day. We looked at the thermal inversion. That would be a good example of being able to explain an environmental concept represented visually. And we looked at describing aspects of a research method, design, and or measure used. Just a reminder to keep looking at all of those emails the College Board is sending you. We're going to start going back over some of those big ideas and more to come during exam prep next week. Thanks so much for joining me as we covered the first half of air pollution. You're done with me for review. Dr. Sowell will be finishing up with indoor air pollution tomorrow. Have a great day, guys. Good luck.